In this video, I want to write the strain tensor in spherical coordinates. In particular, I really want to show you an algorithm to change from Cartesian coordinates to another type of coordinates, not necessarily spherical, but I think that spherical is quite pedagogical because it helps you understand better how to change from one reference frame to another. So, in particular, let's start from the definition of the strain tensor that I have derived previously, but never mind. So here I will just write Uij. So this is capital Uij. So it is a matrix because it has two indices, which is equal to 1/2. Then we have partial derivative of the displacement vector Ui with respect to the coordinate xj, plus, and then you have the opposite. So, I mean, you exchange these two indices to symmetrize this tensor because Uij is equal to Uji. So here you have the symmetric, the other part, which makes the tensor symmetric. So duj dxi. Now, if I want to write it in matrix notation, which will be helpful in this video, I will show you how to calculate the components. In particular, I have done that in Matlab. So I have prepared the script, but in order for you to understand the script, it is necessary to go through some basic formulas without doing explicit calculations, but I think that this is important for you to understand better how to make this kind of switch from one reference frame, from one coordinate system to another coordinate system. So I will write this Uij as a matrix. So it's a U, capital U, tilde. So this tilde will separate vectors from matrices. If you see a tilde here in this video, it means that we are dealing with a matrix. So U tilde is a matrix. It is equal to 1/2. And then how do we express this in vector notation? In particular, Ui, the displacement vector, will be U with this arrow to denote the fact that it is a vector. And when you see a vector like this, it is a column vector. In particular, this would be ux, uy, uz, like this. So if we want to get a matrix, because this is a matrix, you can see that you have two indices. We have the gradient expressed as a column vector, but u must be transposed. So we get u transpose like this. So maybe I can write it like this. So if you think about it, if you consider the gradient vector d over dx, d over dy, d over dz, and you multiply this vector, this column vector, by a row vector, you have ux, uy, uz. If you do this multiplication, you get a matrix. If you think about it, a 3 by 3 matrix. So basically, this is a matrix, and of course, this must be a matrix. And then after you get the matrix, you can do the same thing here, but you take the transpose of this, and you can define this object u like this. Now, this is the definition in Cartesian coordinates. How do we switch from Cartesian to another reference frame? In particular, what I'm really interested in is the object u prime in spherical coordinates, where this is defined as u r r, u r theta, u r phi, and so on. So this would be u theta r, but it is symmetric, so I can still write u r theta if you want, or u theta r, it's the same. U theta theta, u theta phi, and then you get the idea. Here you have u phi phi, and so on. Okay, so it's symmetric. Whereas this uij, so in Cartesian coordinates, this would be uxx, uxy, uxz, and you get the idea. So uyy, and so on. So we really want to express, so we want to find the components urr expressed as some derivatives with respect to r, with respect to theta, or with respect to phi, of the displacement vector in spherical coordinates as well. So the displacement vector u can be written as ux times I, which is the unit vector along x, plus uy, and then we have j, the unit vector along y, plus uz times k, the unit vector along z. But this can also be expressed in spherical coordinates, so we can write ur times the unit vector along r in a spherical coordinate system. Then I will say something more about the spherical coordinate system. U theta times the unit vector along theta plus u phi times the unit vector along phi. Now, this can also be expressed in matrix notation like this. We have r written, so this is the vector r along the first column. Then we have theta in the second column and phi in the third column. This multiplies ur, u theta, u phi, like this. Now, this is also equal to the same thing in Cartesian coordinates. So you have I, j, k. But if you think about it, this is just the identity matrix because the vector I is just 1, 0, 0, and then j is 0, 1, 0, and then k is 0, 0, 1. So it's the identity matrix, the 3 by 3 identity, and then this multiplies ux, uy, and uz like this. Now, in my notation, this vector here will be u prime, and this matrix will be the matrix E prime. And we will write this matrix because we need to use it to switch from one coordinate system to the other. So this is quite important. From here, you can see that U can be written as E prime, U prime. So this is an important transformation that we will use. So we need to find really these coordinates here. This vector U prime will be considered as a function of r, theta, and phi. And when you do this switch, when you make this switch, you can express the coordinates ux, uy, uz in terms of ur, u theta, and u phi. Once you do that, basically you can substitute this formula in here, but we also need to transform this gradient operator, and we also need to transform this u, because remember that this u here is written in Cartesian coordinates. We need to go from u to u prime tilde if you want. So capital U, to tell apart this u here, which is a capital letter, from the vector u, the displacement vector. Now, from here, let me say something more about the spherical coordinate system, some basic things which you should be familiar with if you want to really understand this video. We have the three axes x, y, z, and then in spherical coordinates we have a radial vector r, but if we normalize it, we get the unit vector along the direction r. So this is the radial direction. It's a generic direction that you use in a spherical coordinate system. Now, if we project this vector on the xy plane, we get something like this. And if we measure the angle that the projection makes with the x-axis, I will define it as theta. This is also known as the azimuthal, it's difficult to pronounce, but azimuthal angle, something like that. So it's called azimuthal angle. And in some other sources, this angle here is called phi. So pay attention to that because some references usually use phi instead of theta, but I prefer to use theta because I have grown up by using theta for the azimuthal angle. And I have used phi for the polar angle. So this is the polar angle, the angle measured with respect to the z-axis, right? So as I said, in other sources you have theta here instead of phi, and instead of theta you have phi. So it's the opposite, but this is notation, and this is the notation that I will stick to in this particular lecture, in this particular video. Now, you can do the math. It's quite straightforward. It's well known in multivariable calculus. I will not get into this. R can be expressed in terms of the usual unit vectors along x, y, z, and in particular it can be written like this. It is I times cosine theta sine phi plus j times sine theta sine phi plus k, and then you have cosine phi here. Similarly, you have theta. Now, once you calculate r, you can obtain theta from taking the derivative of r with respect to theta. So if you take this partial derivative of r with respect to theta, you're going to get something, a vector, which is going along the theta direction, and it is perpendicular to r. But we also want to normalize theta because we want theta such that its norm is equal to 1. This is particularly convenient because it will make our vectors with a unit norm. So the matrices that we will construct from them, they will be orthonormal. And orthonormal matrices are quite important because they simplify the calculations. The inverse of an orthonormal matrix is equal to its transpose. So that's why they are important, because they simplify calculations quite a lot. You can check that if you divide this vector by the sine of phi, you will get a unit normal, a unit norm vector. And if you do the math here, so if you take this derivative and you divide by sine phi, you get minus I sine theta plus j cosine theta. So it's quite easy to see that this vector has unit norm. Then we can calculate phi similarly. So we take the partial derivative of r with respect to phi, and in this case one can show that this is already unit norm. If you calculate this partial derivative, you don't need to multiply by any factor here to make it unit norm. So you have I cosine theta cosine phi plus j sine theta sine phi, and finally you have minus k sine of phi. Now these vectors here, from these vectors you can construct a matrix basically. Why do we need the matrix? We need it because it appears here in this transformation, and it will also appear in the transformation of the matrix u tilde into u prime tilde, u tilde prime, whatever you want to call it. So we need to write down this matrix that I called E prime. So E prime, let me write it here, is equal to the matrix that we construct from R, theta, and phi. And you can construct this matrix from what we obtained in here. So basically, we have the components of R written with respect to the three unit vectors along x, y, and z. So we have the cosine of theta, sine of phi. Then we have sine theta, sine phi, and cos phi. So they are the three components of R with respect to the three unit vectors along x, y, z. Similarly, we can write down the components for theta. So we have minus sine theta along I, cosine theta along j, and 0 along z. And similarly, we have phi. Phi is given by cos theta, cos phi. So these are the angles, and these two are the unit vectors along those directions. So pay attention also to these details. We have sine theta, sine phi, and then we have minus the sine of phi. And this is how we construct this important matrix here, which will help us do all the calculations. Now, how do we construct the transformation of the matrix U tilde into U tilde prime. Basically, how can we define U tilde prime? Well, we have to use the usual rules for tensors, or in this case, matrices. So you can write down the transformation rules by thinking about, by thinking in terms of tensors or thinking in terms of matrices. Usually, to construct the transformation for a tensor, you start from an invariant. This can be done in different ways, but since I'm going to use this matrix notation, I will write down an invariant quantity by using matrix notation. So, in particular, I can take, for example, the vector u, I take its transpose, and then I have the matrix u tilde, and then I apply this matrix to the vector u. So what I'm doing this basically, what I'm doing here is this. I take the dot product with u, and I have the vector u tilde u, and I take the dot product with u, like this. This is an invariant because it's a dot product. So in the new reference frame, this should be equal to u prime transpose u tilde prime u prime. So u prime, if you remember, is this vector here. So u prime is equal to e tilde prime inverse u. But if you recall, now this matrix here is orthogonal because we have constructed the matrix from orthonormal vectors. So it means that the inverse is equal to the transpose. So we have E prime transpose U. This is the transformation. So in here, we can either substitute the definition of U prime transpose in terms of U and the matrix E prime by using this, or we can also substitute the expression for U in terms of E prime and U prime. So it's the same because that will lead us to the same conclusion. And for example, I can use this one. Let me show you. That's equal to U transpose, U is equal to E prime, U prime, and then I have to take the transpose of that, if you recall. So I'm using this definition here. And now I will leave U tilde here, and then I will also have to substitute E prime, U prime in place of this U here. This can also be written as this transpose here is equal to U prime transpose, E tilde prime transpose, U tilde, E prime, U prime. And now, since this should be equal to this, it means that U tilde prime is equal to E prime transpose U E tilde prime. So we get this formula, and now we have to use the definition of U tilde. So we have E tilde prime transpose. U tilde is equal to 1/2. Now I will not substitute the expression for the gradient yet because we have to find it. Remember that U tilde is equal to the derivative with respect to this vector x. So this is really the gradient d over dx, d over dy, d over dz, written as a column vector. But we have to be careful because we have to rewrite this in terms of the variables. Partial derivatives with respect to theta, partial derivatives with respect to phi, and also the partial derivative with respect to r. But remember that here we also have U transpose, but for U transpose we already have a formula because we can use the one in here. So we have E prime U prime e tilde prime u prime, and we have to take the transpose of this, and then here we have the same thing, p over dx e tilde prime u prime transpose, and then we have to take the transpose of the overall matrix resulting from this calculation. And finally here we also have e tilde prime, remember that. Now we only need to do one last thing, we need to transform this gradient. After that we are ready to start seeing the results of the script that I have prepared. I have prepared the script such that it implements the formula that you see here, but we still need one last step. We need to find how to write this gradient in spherical coordinates. And how to do that? Well, in general, we have the so-called nabla operator, which is the gradient written in generic coordinates. This can be written as d over dx I plus j d over dy plus k d over dz. This can be transformed in spherical coordinates. It's an exercise that one can see in a multivariable calculus, for example. It's also possible to tackle this by using tensors, but this is not the point of the video. I assume that you know how to transform this into spherical coordinates. I mean, I will take this for granted for this video because otherwise it would be too long. But basically, we can write this operator in spherical coordinates, and I will write down the expression. It's equal to r d over dr plus phi 1 over r d over d phi plus, then we have the vector, the unit vector theta, 1 over r sine phi d over d theta. One can derive this expression here. And this expression can also be recast in a different form. So in matrix notation, we have r phi theta applied to the vector d over dr, 1 over r d over d phi, and 1 over r sine phi d over d theta. And what is this? So this can be written in the following form. In particular, it is e tilde prime, and then we have the operator d over dx prime. So I define basically this vector as d over dx prime. So I can substitute this expression in here. So I have to transform this, and I can do it in here. So I can put e tilde prime, and this would be d over dx prime. So this is written in spherical coordinates. And similarly in here we have e tilde prime d over dx prime. And this is the final formula, so the formula that we will implement in Matlab without doing the calculations ourselves, because these are really, this can be long calculations. So I don't want to do them because I want to show you the intuition, so the logic, the mathematical logic behind this, and then we will let a calculator, in particular Matlab, do all the job instead of us doing all the calculations by hand, because this is really painful. So remember that this expression is equal to u tilde prime. So u tilde prime is the matrix containing the components of the strain tensor in the spherical coordinate system. So it contains urr, ur theta, ur phi. So you can see the components written here. Whereas u tilde contains the components written with respect to the Cartesian coordinate system. So you have uxx, uxy, and so on. Now let's go to Matlab. I have prepared the script, so I have defined some symbolic variables. In particular, I have already run the script, but I mean, to do the math, you need to define the symbolic variables. I have defined phi, I have defined theta, r, and then I defined u prime. Lowercase u prime is the displacement vector in a spherical coordinate system, whereas capital U prime is the strain tensor written in the spherical coordinate system. And then we have E prime, which is the matrix that I also define in here. I define the matrix by components, and then I define U prime as U sub r, U sub theta, and U sub phi. That, I mean, U sub r, U sub theta, and U sub phi are also defined as symbolic variables. And then I do the calculations. In particular, here, these coefficients A1, A2, and A3 are basically the partial derivatives of U prime, E prime. So I'm doing these calculations here. So basically the logic is the following. In the script, first I calculate these matrices, I take the transpose, and then I take these derivatives, and when I do that, the result is contained in this vector. I mean, this is actually a matrix, in this matrix B. So the calculation is here in these lines of code, these lines here. And then I multiply the matrix B by E prime here. So the multiplication that you see is this one, this multiplied by this other matrix. And then I also have to take the transpose of that. So I call this matrix C, and of course this would be C transpose. And then you can see that the final formula is indeed this one. You have E prime transpose, and the transpose in Matlab can be obtained by this operation. So I have this dot together with this apostrophe, so you get the transpose from doing this, multiply by 1/2, and then you get C plus C transpose times E prime, and you do all the calculations basically, and the result is here. So U prime is in here. For example, the first component, the first entry, the one entry would be U sub r sub r. So U sub r is the derivative with respect to r of U sub r. U sub r is the displacement, I mean the first component, and the component along r of the displacement vector. And similarly, you can get all the other components. For example, this one here would be U phi phi. U phi phi is this. And then you can also get, for example, this one would be U r theta. U r theta is this constant sigma 1, which is shown in here, and so on. So you can see that the matrix is symmetric. For example, you see sigma 1 here in the position 1, 2, and also in the position 2, 1. So the matrix is definitely symmetric. And similarly here, for example, in the entry 2, 2, you get U theta theta, and so on. So you find the expressions for all the components of the strain tensor written in spherical coordinates. And this logic can also be applied in other reference frames, in other coordinate systems, for example, in cylindrical coordinates, and so on.